Welcome everyone, and this is going to go through the video assignments for chapters 17, 18, and 24. The tests using quantitative data that we're going to see in the course at least. Alright, so chapter 17 video assignment, this is the one where we're working with the one sample t-test, right? And so then t-test and actually the one sample confidence interval, or confidence interval for the mean. And so we have some information given about a quantitative variable x. We have an SRS of 16 individuals. I forgot to write that down. So we have a sample size of 16. And let's see, so for this sample, right, we have a sample mean. We should actually clarify that this is the sample mean of 12. And then this is the sample standard deviation of 2. Come from a population where the characteristic x is normally distributed. Interested in testing the claim that the population mean is greater than 10. And so this 10 is going to be our hypothesized mean, hypothesized population mean. And so 5% level of significance. Okay, so part A, it says determine the 95% confidence interval for the population mean. So we know that a CI, right, that it's going to look like x bar minus our margin of error, and then it's going to be x bar plus our margin of error. Okay, and so here the sample mean is our x bar. Okay, so that's the easy part. Now we need to figure out what E is. Okay, E is our margin of error and is not just the standard deviation, right? So using a formula, right, it would be this T star value. It's a T alpha over 2. There's a bunch of subscripts, but we're not going to worry about finding this by hand so much. And then you would multiply that by your standard error, which would be s divided by square root of n. So if you wanted to do it by hand. If you want to just use Excel, there's confidence.t. And I'll scroll over so we can actually zoom out maybe just a smidge, or it's not going to let me. That's lovely. Confidence.t, and then we need to specify alpha, which was back here, 0.05. Standard deviation, this would be the S that we work with, sample standard deviation. And then the last thing it's going to ask for is size, which is the 16. And so if you do that, you get about 1.06. Okay, so again, if you're following the formula along, the n would be the size and sample standard deviation would be the n. If you want to find that t value, you would just do like t.inv and then specify what the parameters that it needs. I think if we just do t.inv, so probability, that would be connected to the alpha. So the probability 1 minus alpha over 2, so that would be 0.975 here, and then degrees of freedom would be size minus 1, so 15. Okay, and so if you wanted to do that, you could. But just a lot easier to use confidence.t. And then our x bar minus E would then be, sample mean 12 minus this 1.06 number, and then the upper bound would be x bar 12 plus margin of error. There you go. Okay, number 1 done. And so normally you'd have to interpret it, but it doesn't say to do that. It just says determine, so we determined it. Okay, null and alternative. All right, so null, HO, should look something like mu is equal to what we hypothesize, so 10, and then the alternative should be mu is, and then we have to use our claim. Our claim is that the mean is greater than 10. So, and then we should also just say, like, mu is equal to the population mean of characteristic x. Okay, so that would be our null and alternative. Okay, now part C, it says determine the value of the test statistic. Technically, before we do this, we should verify conditions. So is sigma unknown? Sigma is population mean, right? Unknown. Yep. Good. Do we have normally distributed or sample size greater than 30? We have normally distributed. Approximately normal is fine in lieu of normality. Okay, if we see strong outliers or skewness, then we take pause. And then are the samples IID? Yep, we have an SRS. Okay, SRS gives you IID, and then we have the other conditions verified, so we can go forward with the test. And so the test statistic, I'm going to do it over here in Excel, the T test stat, that would be, so numerator, I'm going to put parentheses around it, would be sample mean minus hypothesized mean. Denominator, I'm going to put parentheses around that too, S divided by square root of n. Okay, and generally if people mess up, it is because of the denominator. There's like a denominator within a denominator, so it's actually like one denominator and actually a numerator. So that's why putting parentheses around the entire denominator is necessary. 4 ends up being a nice number. Okay, so that's part C. P-value. Okay, we're going to use a version of t.dist, and which version are we going to use? Is it t.dist, t.dist.2d, or t.dist.rt? Answer, look at your alternative hypothesis. Which is the direction? Mu is greater than is off to the right, so I'm going to use t.dist.rt. Okay, X is our test stat, degrees of freedom is sample size minus 1, at least for a one sample t-test, and I get my p-value, pretty small. Okay, provide the Excel command, so if you need the Excel command, again, it'd be t.dist.rt and then 4, comma, 15. Okay, based on the p-value, state the correct decision. We reject the null hypothesis. There we go. And then normally you go on and interpret, but we're just going to leave that for time purposes. So there you go. There's chapter 17. On to 18. Oh man, this is going to be a long video. Brace yourself, speed me up, or take breaks. All right, here we go. Still SRS. Helps if I change the video assignment. Chapter 18. Okay, and this time we're working with male and female statistics students and their height in 2021. Height is approximately normally distributed. Actually, most natural characteristics in humans are normally distributed, which is super handy. Is there evidence that the mean male statistics student's height is more, well, okay, I mean, yeah, probably. But let's do this with statistics, right? So we're going to write the null and alternative. All right, so I'm going to do HO. HO, I would assume that the mean, the mu for males, is the same as the mean height for females. Oops, equals mu subscript F. All right, and after the null hypothesis, we need to do the alternative. So I'm going to do a simple copy paste here and change a few things around. So change this to alternative, and then also the claim is that the mean male height is greater than the mean female height. And then, of course, if we use a symbol, we should define it. So I'm going to say mu m is the average, let's see, male statistics student height in 2021. And then you could add UMR in there as a descriptor as well. And for females, I'm just going to say average female height. Okay, and that would be our null and alternative. Okay, now part B, it says again, determine the test statistic by hand and confirm with Excel. We will do that momentarily, but before that we should also verify the conditions. So do we have sigma is unknown in both? Yes. Do we have IID? Yes, we have SRS. And do we have approximately normally distributed? Yes. Okay, so we can go forward with the test statistic. Okay, so test stat, and this is where, if you're doing this by hand, I recommend breaking it into numerator and denominator, and then get the test statistic from that calculation. So numerator would be just the difference in the sample means. So actually, before we do that in Excel, I should get all the summary statistics. So data analysis, And in the pop-up window, I'm going to select descriptive statistics. Okay. Input range, these, organized by column, output range. I'm just going to click on a random cell. That one looks good. Summary statistics, check that box. Okay, so we got the mean. All right, numerator is just going to be the difference in the means. So it would be male data first. Okay, typically, if we write, I mean, it sort of depends on your preference. You could also write this as like mu for your alternative mu m minus mu f is mu f is greater than 0. So what I would do is I would do the male data first minus the female, and then that should be positive. Okay. So coming back over to Excel, oops. So we have male average minus female average. Okay, that's the numerator. Denominator would be square root of S1 squared, so that would be the standard deviation for the males, square that, divided by n, so the number, the count, okay, and then plus, okay, the standard deviation of females squared, divided by number of females. There we go, parentheses around all that, being careful to do that appropriately, and then divide the two, so numerator divided by denominator. Oops. Arg. Okay, let's try that again. Numerator, click, divide by denominator. Okay, there we go. And confirm with Excel. So then confirming with Excel, so this is where, we built character doing that calculation by hand, and now we can just do t-test to sample assuming unequal variances, and we always want to do unequal because the unequal accounts for the equal case too. So I'm going to select the male data first as variable 1, variable 2. I'm going to do female data then, and then output range, select a random place in Excel, click, and if I did it right, do I get the same number? I see I have 4.49. Yes, I did it correctly. Yahoo! Okay. And then provide the p-value. P-value is very small, okay? And you could also do, so if you wanted to calculate the degrees of freedom by hand, you could just do t.dis.rt of this as well, as long as you have your degrees of freedom. So you'd get degrees of freedom, whatever that is, and then p-value would be t.dis.rt, and then teststat degrees of freedom, and you'd be good to go. But it's saying invalid because I don't have a degrees of freedom. Okay. And so because your p-value is so small, you would reject the null. Okay? And degrees of freedom, if you don't remember it, feel free to look it up, but it is a very long and arduous formula. Again, so I would break it up into like how we did the test statistics. So get the numerator, get the denominator, divide the two, and move forward. Okay? And actually, even with the denominator, you have a denominator, so be careful, okay, when doing it by hand. You have to do it by hand once in the activities. Okay, moving on to chapter 24 at last, ANOVA. Okay, so multi-sample test of average to see if there's a difference. And so here it's talking about IQ, normally distributed. Okay, 3 SRSs are taken. The data's on the next page. Okay, I also have it copied. Is there evidence that their mean IQ is different between groups of different political affiliations? So typically what we would do is write the null in symbols because it's easier. So it'd be like mu D is equal to mu L for libertarian. So the mean IQs of Democrats is the same as mean IQ of libertarians is the same as mean IQ of Republicans, and then you would, I'm not going to do it this time, you would define each one of those as the average IQ for the respective political party. Now the alternative, it's not as simple as writing not equals between them because we don't know which one is not equal. it could just be that Democrats and Republicans are the same and Libertarians are different, right? Or, some combination thereof. So you'd actually need to write out several different sets of hypotheses. So rather than hurt our brains with all those different combinations, it's just easier to say at least one mu I, and mu I would be Democrat or L, R, or D, is different. Okay, just to account for the different cases. Okay, so that would be our hypotheses after we define those symbols. Now, part B, is the test appropriate? So this is testing for the conditions, right? So one condition is, do we have 3 independent SRSs? Yep, it tells us that. Okay, that's fine. Next condition, do we have approximate normality? Yes, it says normally distributed characteristic. If we weren't given that, how would we do it? We would, highlight the data and, look at a histogram. Okay, well, okay, fine. We maybe need to change the number of bins, right? Change this to like 4 bins or something. And it should change, or maybe, okay. So let's see. I don't think that's going to visualize the best. So there appears to be some skewness. But as long as there isn't really, really strong skew, so for instance, like, data way, like extreme values in the 80s or something, just go with it. But here we're actually given normality. Okay. And then the last condition is the one where we need to do some calculations. So actually what we're going to do is we're going to run the test and then cheat and back up and say, yeah, the condition is verified. So, so two of the first 2 conditions are met, right? So condition 1 and condition 2. This condition, we don't know that the population standard deviations are the same. So that's where we have to check this ratio. Okay, but before we do that, we're going to actually skip ahead and get this information in part C, just because it is a little bit easier to get the data. So we're going to single factor ANOVA, highlight the data, output range there, click OK, and then we get this big old table. Okay, now what I want to do before I go on to C is actually calculate the standard deviation, which is the square root of variance. Okay, and then with this, what I need to do is I need to take largest s divided by smallest s. Okay, so largest is this one, divide by smallest is that one, and make sure that that's less than 2. And it is. So then that last condition of the ANOVA test is satisfied. Coincidentally, we also get answers for part C. So we have the F value, 0.13, which is actually good to see. That we want F to be close to 0. Okay, closer it is to 0, the higher the p-value we get. We get degrees of freedom of the numerator. That's the between groups. Within groups is 27. If you're interested in these, feel free to read up, or you can ask me at Just Ask or something. P-value is there, so we would fail to reject the null since P is high. Okay, so we'd fail to reject the null, and we have at long last completed our video assignments. Okay. So again, with ANOVA at least, checking the conditions, it is sometimes easier to actually run the test and then look at the summary output and figure out, okay, did ANOVA actually work here? Like, can we do it? And that sort of validates everything that we get after that too. Okay, so as you continue your work, always make sure to check your conditions. Define your symbols and your hypotheses. Those are typically the 2 stumbling blocks that we run into. Otherwise, have fun.